Why does your blood pH change every time you eat or drink something that's acidic? The answer is buffers. In this video, you'll learn exactly how they work and how to calculate their pH. In the last video, we examined the equilibrium concentration of ions in solution containing weak acids and bases. In today's video, we'll explore these solutions containing a weak acid or base combined with a soluble salt of that acid or base. So, refresher from yesterday, we said that something like acetic acid, when placed in solution, will ionize into an H plus aqueous and an acetate ion. So this is a weak acid, and this is a conjugate base of that acid. Today we're going to explore what happens when I add a salt, which has a common ion in it. So the salt we're going to be using will be sodium acetate, and it's a strong electrolyte. So it's going to produce sodium ions and acetate ions. All right, the sodium ion has no effect on pH. So we said this was a strong electrolyte. So what essentially happens is, by the adding this, my amount of conjugate base increases. As my amount of conjugate base increases, it's going to force this entire reaction further to the left. In doing so, I will have less H plus in the initial reaction, so therefore the pH will be higher. If I add more acid, then the reaction will shift to accommodate this. The rule is that when a weak electrolyte and a strong electrolyte contain a common ion, the weak electrolyte ionizes less than it would if it were alone in solution. This is called the common ion effect. These types of solutions are also called buffers or buffered solutions. A buffer resists changes in pH because it has both acidic ions to neutralize OH ions and basic ions to neutralize the H plus ions. So it helps to maintain a more constant pH, and the pH doesn't fluctuate over large amounts. Okay, in our first problem, we're giving a sodium acetate mixture with acetic acid. And we want to know what the pH is. Okay, so let's do it. Let's do this problem twice. Let's do it once with the sodium acetate and once without the sodium acetate. So let's go ahead and do it first without. So CH3, COOH. We'll start off with an ice table. Okay, as I said earlier, we're going to do it without the sodium acetate. So this is going to be 0.3, 0 and 0, minus x, plus X plus X All right, since the Ka is 10 to the negative fifth power, and this is 0.3, that means there's 4 powers of 10 difference, so we can ignore the minus X part. All right, so the Ka is equal to concentration of the H plus times the concentration of the acetate divided by, and the Ka is 1.8 times 10 to the negative fifth. So X squared is going to be equal to, I'll multiply those together, I will get 5.4 times 10 to the negative 6. So this will be 0.00232. So the pH will equal the negative log of this. So the pH would equal 2.63. Now this is without the sodium acetate. Okay, now let's do it with the sodium acetate. Okay, so I'm going to make a few changes. I'm going to change this number, change this column here. So I have 0.3 moles. Again, this will be plus X. This will be 0.3 plus X. Again, I'm going to ignore the plus or minus X's because there's so many powers of 10, like 4 powers of 10 difference. So that's insignificant. So the Ka is equal to X times 0.3 over 0.3. 0.3's cancel. So X is going to equal to Ka. So the pH is going to equal the negative log 1.8 times 10 to the negative 5. So the pH is going to equal 4.74. So this is with the salt. This is without. Okay, I have a formate ion concentration and pH from a 0.05 molar formic acid and a 0.1 molar nitric acid. All right, so let's write an equation for the weak electrolyte. Formic acid H plus formate ion. Again, we're going to do an ice table. I know the Ka here is 1.8 times 10 to the negative 4. The common ion this time is going to be the H. So my acid will be 0.05. My strong acid is going to fully ionize. I have no formate ion in the beginning. The change is going to be minus X plus X plus X. Will be 0.05 minus X, 0.1 plus X, and X. So H plus is a common ion. There's 3 powers of 10, so it's okay to drop the plus X. So Ka is going to equal 0.1 times X over 0.05. And we know the Ka here is 1.8 times 10 to the negative 4th. So when I multiply this out, I will get 9 times 10 to the negative 6 equals 0.1x. So x is going to be equal to 9 times 10 to the negative 5. pH is going to be the negative log of 9 times 10 to the negative 5. So the pH is going to be 1. So notice there that the addition of this nitric acid took full control of the reaction. The formate ion had very little effect, if any. Okay, the Henderson-Hasselbalch equation. This equation helps you to solve buffer problems much easier and much quicker. So let's go through and I'll show you how it works. Okay, so I have a weak electrolyte, okay, HX. So it's going to break apart into H plus and X negative aqueous ions. So Ka is going to equal the concentration of H plus times X negative over HX. We know that pH is equal to the negative log of the H plus. So let's take out the H plus in this equation here. So if I take out the H plus, it's going to equal the Ka times concentration of HX over the concentration of X negative. Okay, let's take the log of everything. So the log of H plus equals the log of Ka times the ratio of concentration of HX over concentration of X negative. So this would be the log of H plus equals the log of Ka minus the log of HX over X negative. Okay, I know that the log of H plus is pH. The log of Ka is called the pKa. That's going to equal the pKa minus the log of the ratio of the Hx to the X negative. Okay, I do not like having a negative sign in my equation, so I tend to forget to put it in there. So let's rearrange this a little more. So pH is equal to pKa plus log. If I change the sign, I had to flip this over. So this will be X negative over Hx. So let's refine this one more time. So pH is equal to pKa plus log. All right, this is my conjugate base over my acid. All right, so this is the Henderson-Hasselbalch equation that I like to use. I would suggest memorizing this. Calculate the pH of a buffer composed of a 0.12 molar benzoic acid and a 0.2 molar sodium benzoate. All right, so we're going to put our weak electrolyte. We'll write it down as C6H5COOH. It's breaking apart into the H plus and the benzoate. What I do when I work these type problems is I label everything. So I have 0.12 molar of this one. I have 0.2 molar of this one. I know that my Ka is 6.3 times 10 to the negative 5. So now I'm just going to plug and chug. So pH is equal to the pKa plus the log of the base over the acid. I'm looking for the pH. pKa will be the negative log of 6.3 times 10 to the negative 5 plus the log of the base, which is going to be 0.2, divided by the acid, which is 0.12. So the pH is going to equal, this is 4.20 plus, so my pH here is going to equal 4.42. Not only can we solve for the pH, but we can use the pH to solve for other parts of the problem. In this example, you're given the pH. pH is 4, and I need to know the amount of salt that will give me that pH. So let's go through and label everything again. So C6H5COOH. H plus, and the benzoate. Okay, so I want a pH equal to 4.00. My Ka is 6.3 times 10 to the negative 5th. So I'm looking for this. Don't know what that is. But I know that this is going to be a 0.20 here. All right, so starting with Henderson-Hasselbalch, so we start with 4.00 equals the pKa negative log 6.3 times 10 to the negative 5 plus the log of the base over the acid so the negative log of 6.3 times 10 to the negative 5 is 4.20. Plus the log of x minus the log of 0.2. I'm going to take this to the other side, and I'm going to take this to the other side. In doing so, I would get negative 0.899 equals the log of x. All right, so to get rid of this, I'll raise both to the power of 10. So x is going to equal 10 raised to the negative 8.99. So x is going to equal 0.126 molar. And let's go ahead and just round that then to 0.13 molar. All right, so that'll be the concentration of the sodium benzoate that I would need. Okay, this equation, we will have ammonia and it's going to be reacting with water. To produce ammonium and hydroxide. All right, so my desired pH is going to be 9.00. My Kb is going to be equal to 1.8 times 10 to the negative 5. All right, I'm working with bases this time. So my Henderson-Hasselbalch for base, I'm going to use the POH is equal to the pKb plus the log of the conjugate acid over the base. So you can see it's slightly different. All right, so some things that we need to know. pH plus POH is equal to 14. So POH is equal to 14 minus the pH, which is 9. So that's going to be 5. 5 is equal to the negative log of the pKb, or the Kb rather, 1.8 times 10 to the negative 5 plus the log. Okay, I do not know the acid, but I do know the base is 0.1. So this is 4.74. Go ahead and break this other part. Log of x minus the log of 0.1. We'll take this to the other side, and I'm taking this to the other side. So I'm going to say 5 minus 4.74 minus 1 is going to equal the log of x. So this is going to be negative 0.74 equals the log of x. Just raise it to both sides to the power of 10, or take the antilog. So x is going to equal 10 raised to the negative 0.74. So I get x is equal to 0.182. All right, so it says that we have 2 liters here, okay? So I need to multiply this by 2. So that means that my x will be 0.36 or 364. That should be my answer. So what happens to a buffer solution if I add a strong acid or a strong base to it? Okay, let's explore that. All right, so acetic acid okay, before I add the HCl, let's do it here on the left side. So the pH is equal to pKa plus the log of the base over the acid. All right, so the negative log, 1.8 times 10 to the 5th, plus the log 1 over 1. So the pH is equal to 4.74 plus 0. So the pH is equal to 4.74. Now that's without adding my HCl. Okay, after adding, okay, Henderson-Hasselbalch again. All right, here's where it changes. All right, if I'm adding acid, my base will diminish or decrease by the amount of strong acid that I'm adding. So this is 1. I'm going to subtract 0.2 from that. The amount of acid will increase by the amount of strong acid that I'm adding. So I'm going to add to the acid part. So this is 4.74 plus a log of 0.8 over 1.2. So this gives me a pH of 4.56. Now, if I were doing a base, I would do the same thing. So if I were to add a strong base, I would add here, and I would subtract here. So that's all you have to do to alter the Henderson-Hasselbalch equation if I'm adding a strong acid or a strong base. Let's predict whether a salt is an acid, base, or neutral. Okay, what is a salt? Well, salt contains a cation and an anion. The cation comes from the base. The anion comes from the acid. When an acid and base combine to form a salt. If the acid is strong, and the base was weak, then it will be acidic. The salt will be acidic because the acid effect is stronger than the base's effect. If I have a weak acid and a strong base, then it's going to be basic. If I have a strong acid and a strong base, then the salt is going to be neutral. Both are weak. I had to compare the respective Ka and Kb's to determine which one has the greater influence. So if the Ka is larger, then it's going to tend to be more acidic. If the Kb is stronger, then it's going to be more basic. All right, let's try some examples. All right, which of the following will have the lowest pH? All right, NaNO3 or FeNO3 3. KBr or KBRO. CH3 NH3Cl or BaCl2. And let's do one more, NH4NO2 or NH4NO3. So let's predict which one will have the lower pH. Strong base, strong acid. Weak base, strong acid. So that lower pH. Strong base, strong acid. Strong base, weak acid. All right, so this has to be the one, won't it? Because this is neutral, while this one is a base. So neutral is lower than base. All right, on this next one. I know that my acid here is a strong acid. This is a strong acid. Okay. Weak base, strong base. So I know this is going to be neutral. So therefore, this has to be the stronger acid. Weak base, weak acid. Weak base, strong acid. So it has a stronger acid, it has a lower pH. Okay, to calculate the pH of a salt. All right, first off, we need to know that Ka times Kb is going to equal Kw. Kw here will be 1 times 10 to the negative 14th power. Or I can say the pKa plus the pKb is equal to 14. So if I know that the Ka for acetic acid I know that's 1.8 times 10 to the negative fifth, then what is the Kb then for the acetate ion? Well, it's going to be 1 times 10 to the negative 14 divided by 1.8 times 10 to the negative 5. So it's 5.5 repeating times 10 to the negative 10. This is the Kb for the acetate ion. Okay, let's try another one. The Kb C6H5NH2. If this is 4.3 times 10 to the negative 10, so for its ion, C6H5NH3 plus, the Ka then be 1 times 10 to the negative 14 or 4.3 times 10 to the negative 10. So that will be 2.32 times 10 to the negative 5. So we'll use this little trick to calculate the pH of salts. All right, let's actually try a salt here. So I have potassium cyanide. It's a solid. Okay, so if I were to dissolve this, I would get K plus aqueous plus Cn negative aqueous. Okay, I know that this is neutral because it comes from a strong base. I know that this is a basic ion. We're given here that the Ka for cyanic acid is 4.9 times 10 to the negative 10. Okay, let's do a little ice table here. All right, so Cn negative plus water All right, so my CN negative concentration will be 0.500. Okay, I don't consider water at all. I have none of those initially. Minus x plus x plus x. 0.500 minus x, x, and x. So I know that Kb is going to be HCN concentration times the OH negative concentration over the CN negative concentration. So I'm going to say 1 times 10 to the negative 14 divided by 4.9 times 10 to the negative 10. So that's going to give me my Kb of 2.04 times 10 to the negative 5. All right, so let's substitute into this equation here. So it would be 2.04 times 10 to the negative 5 equals x squared over 0.05 minus x. Again, we can not do this because of the huge number of powers of 10 between the two. Solving for x, I'll get 0.001. So the POH is equal to the negative log of 0.001. So the POH is equal to 3. So the pH then will be 14 minus 3, which equals 11. That means that this salt will have a pH of 11. All right, so we have another salt, ammonium chloride. So ammonium chloride solid gives me ammonium and chloride. Okay, this is an acidic ion. This one is neutral. Because it's from a strong acid. And I know that my Kb for ammonia will be 1.8 times 10 to the negative 5. So let's write out that reaction. We have ammonium plus water will give you ammonia plus a hydronium. Here's to our ice table. Now I don't do anything with the water. All right, so the initial concentration of the ammonium will be 0.2. And 0 of these minus x plus x plus x. 0.2 minus x, x, x. So Ka is concentration of the NH3, concentration H3O plus over the ammonium. I know that Ka will be 1 times 10 to the negative 14 divided by the Kb, which is 1.8 times 10 to the negative 5. Gives me a Ka of 5.6 times 10 to the negative 10, very small number. So 5.6 times 10 to the negative 10, I'm plugging into this equation here, is equal to x times x, or x squared, divided by 0.2. I'm disregarding this because it's so tiny. So I'm solving for x. I get 1.05 times 10 to the minus 5. So pH is equal to negative log of 1.05 times 10 to the negative 5. So my pH is equal to 4.98. Which would be the pH of ammonium chloride. At this point, you should be able to explain how buffers resist changes in pH, use the Henderson-Hasselbalch equation to calculate pH, and adjust for additional strong acid or strong bases. If all of this makes sense, you just mastered one of the most important topics in acid-base chemistry. In the next video, we're going to apply everything you've learned here to titrations, where you'll see buffers show up in real time on a titration curve. That's where this really starts to come together, and I'll see you in the next video. Goodbye.